All right, so day one, we're going to talk about sets. And so the first idea I want to talk about is this whole idea of sort of well-definedness. And so what I want to do is I want to introduce what I'm going to call a collection for now. So let's consider the following collection. So this collection contains the number 1, the number 2, the number 3, and the number 4. Now, when I talk about this idea of well-definedness, what I mean is at any point in time, can I tell precisely and articulately what's in the set? And I can, right? Because I know for certain 1 is an element or a member of the set. I know that 2's an element or a member of the set, etc. And I also know what's not in the set, right? I know that 5's not in the set. And I know that the number pi is not in the set. I know that negative 3/4 is not in the set. So this sort of hints at the idea of well-definedness. At all times, I want to be able to state precisely what's in my collection. So this is going to be something that we're after. A collection where we can describe all the members and, in a sense, all the non-members. Let's consider the following collection. So let's consider the collection of some blue cars. So I hope you can start to see the issue here, right? So you know that this collection has blue cars in it, but which blue cars? We can't say, right? It's super vague. So consider the collection of some blue cars. That's not a well-defined collection. I can't tell you precisely what's in that collection and what's not in the collection. And so this is exactly the problem here that we want to avoid in mathematics. So this is vague, and that makes us sad. So this is not a collection that we really want to consider. And so definition, I'm hesitant to call this a definition. If you study more math, you'll talk about why, but I'll call this a sort of definition. So a set, that's what we want to define. A set is a well-defined collection of objects. Okay, so yeah, as we mentioned before, this collection, this would be considered a set. It's well defined. I know precisely what's inside of the collection, and I know what's not inside the collection. That's good. That would count as a set. This collection was problematic because its description was vague, and we did not know precisely what's in the collection and what's not. So we would not consider this a meaningful set. So this is not a meaningful set where this is. I want to note something. So let's note the objects that are inside of the set. We call these elements. So 1 would be an element of the set, 2 is an element of the set, etc. So yeah, let's say that precisely. So the objects or members, right? So the objects inside a set are called elements. And so we could say precisely, well, we could say that 1 is an element of the set containing 1, 2, 3, 4. I could say that 2 is an element of the set containing 1, 2, 3, 4. 3 is an element of the set containing 1, 2, 3, 4. And 4 is an element of the set containing 1, 2, 3, 4. And notice that these squiggly braces are one way we define sets in mathematics, or denote them rather. But I could also say something like, I could say that pi does not belong to or is not an element of the set containing 1, 2, 3, 4. Okay, so notice how we use this sort of membership notation. So 1 is an element of the set, or 1 belongs to the set, or 1 is a member of the set. Pi does not belong to the set. One thing I want to note when it comes to sets is that we don't really distinguish between something like this. So here I want to sort of look at the idea of repetition of elements. So suppose I had the following. We don't really consider the repetition. We really think of the set in the following way. The set containing 1 and 2. I know that's different than when you study a sequence, but with sets, this is how we deal with repetition. Okay, so there's a couple ways to denote sets. We have this so-called list or roster method. So for example, let's say I've got the following set. Let's say I've got the set containing the following letters: N, O, I, S, and E. So this is a 5-element set. Another way to describe the same set is with the set builder notation, which can be very handy. So here, so I'm going to read it and then sort of talk about how to think about it. So this is the set of all elements X such that, or with the property. So after this such that bar is going to be a property that all of these elements will have. So this is the set of all elements X such that X is a letter in the word noise. Okay, so let's think about that one more time. So this is the collection or the set of all objects X such that X is a letter in the word noise. So you might want to ask yourself, when you get such a set, what do the elements look like? Well, the elements look like letters in the word noise. And of course, we don't count any repetition. So I wouldn't write, N, O, just everything is counted once. That's a big idea in mathematics. You always want to understand the objects of your set. What does your set look like? What does the collection look like? And so now we want to talk about some very, very important sets in mathematics. And one, I want to talk about a very special set called the empty set. This is the set that has no elements. So the empty set. So the empty set is the set containing no elements. And at first that might seem kind of strange, but you can think about this sort of metaphorically. You can think about this as maybe like a grocery bag with nothing inside of it. So if you think about it in that way, it's got sort of the shell or the casing of the set, but no members or elements. The way we denote the empty set in math is this sort of circle with a line through it. So every time you see that, that's the set containing no elements. Sometimes we write it like this. So exactly a set with nothing inside. Okay, so that's the empty set. Notice it's empty. And then sometimes sort of a clever way to write this is the empty set is equal to the set of all objects x such that x is not equal to x. Well, if I tried to collect all the objects that aren't equal to themselves, well, every object is equal to itself, so therefore there's no objects in here. So therefore this must be the empty set. So that's an alternate way to denote the empty set. I'm going to sort of break this off from the rest of the sets, because really right now what we want to do is talk about classic number sets. And so now we want to talk about the set of all natural numbers. And so we denote this by n with a bar on the left, n bar. So as soon as I see this notation, I know instantly, oh, that's the set of all natural numbers. Notice that there's a least or smallest element, and that's 1. Now, in some fields of mathematics, the natural numbers are defined at 0. That's actually fine too. You don't lose any properties, and the structure remains. Also, I think in computer science, a lot of computer scientists define this to start at 0. That's fine. It's really not a big deal. It just depends on how you're defining the set to start at 1 or 0. But the big thing you want to realize is that to get to the next element, you just add 1 to the previous. The ellipsis, the dot, 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 implies that this pattern of increasing by 1 goes on forever. And in that way, this is an infinite set, because any natural number I think of, I can always add 1 to it to get to the next one. So it's infinite. Now, one thing you're going to notice about this set is if I take any sum, if I take 2 elements in the set and I compute their sum, like 4 plus 2 is 6, that sum is back in the set. 3 plus 2 is 5, 3 plus 1 is 4, 4 plus 100 is 104, and 104 would be back in the set. Eventually, it's in there. But in some sense, this set has a problem. It has an issue. If I start taking differences, watch what happens. Now, 3 minus 1 is okay because its difference is back in the set. But if I do 1 minus 3 is negative 2. Negative 2 is not in the set. It's not in the set of natural numbers. So in this way, we actually say that the set of natural numbers is not closed under subtraction, meaning if I pick any 2 natural numbers, I'm not guaranteed that the difference is back in the set. It sure would be nice to have a set where if I took any 2 elements and computed their difference, the result would be back in the set. That doesn't happen here. We're going to fix that with the next set. This is the set of all integers. So the notation we use is this z bar. And that's equal to the set containing, well, I'm going to have a dot, dot, dot on the left, comma, let's say minus 2, minus 1, 0, 1, 2, 3, 4. And this extends forever to the right. Now, it may seem kind of strange to you that this is the set of integers, or all integers, and we're using the notation z. Well, this comes from the word Zahlen, which is German for numbers. So in a sense, this fixes that one issue that the set of all natural numbers had. Remember, if I took any 2 natural numbers, I wasn't guaranteed that their difference was back in the set. But here, this is quite good because if I take any 2 integers and compute their difference, that difference is back in the set. We say the set is closed under subtraction. And you can see that, right? So 1 minus 4 is -3. That's in there. It's over here. It's in the ... land, but it's in there. I could, of course, could do, 4 minus 0 is 4. That's back in there, etc. So yeah, for any two integers I pick, their difference is back in the set of integers. Well, I could do multiplication here. That seems nice. But what happens if I try to compute quotients, if I try to do some division in here? Well, 4 over 2 is 4. That's back in the set. But what happens if I do something like 3 divided by 2 or 3 over 2? Is 3 over 2 back in the set? It's not. That's an issue. We want to resolve that. Notice that each set we introduce sort of clears up or resolves an issue that the previous had. That'll be a common theme here. Now 4, I'm going to start this. It's a bit trickier than the others, but we just need to think about it in the right way. So this is the set of all rational numbers. Notice that the word ratio or fraction is in the word rational, right? So we should expect ratios or fractions. The notation that we use is this Q bar, Q for quotient. And so the set of all rational numbers is equal to the collection of all numbers R, such that R is equal to A over B, where A and B are integers. And of course, we don't want to divide by 0. So B is non-zero. So yeah, this is the collection or the set of all elements R, such that basically R can be represented in this fraction of integers, this ratio of integers, integer over integer form. So any number that can be expressed or written in integer over integer form, where of course the denominator is not 0, that would be a rational number. And this is the collection of all such rational numbers. So I said earlier, it's a good idea anytime you're presented with a set, particularly in set builder notation, to take a step back and try to understand what its elements look like. That's essential. Let's do that. What do some elements of the set look like? So let's make an observation. Let's note that the number 4/5 is a rational number, exactly because 4/5 is expressed in integer over integer form. And then we say, well, this is true, so let's justify it, since 4/5 is the quotient of integers. Or I could say a ratio of integers. What about -17? Is -17 a rational number? Let's go back to the definition. If I'm unsure, I could just say, okay, a number is said to be rational if I can express it in integer over integer form. Am I able to express this in integer over integer form? Yeah, for sure. We can put it over 1. If I write this as -17 over 1, it'd certainly be an integer over integer form. And that's the requirement to be a rational number. Yeah, so -17 is an element of the set of rational numbers, since -17 is equal to -17 over 1, integer over integer. Okay, that's the form you're looking for with a rational number. Well, you could actually extend this thinking a little bit. So let's note something. Let's go back to our sets. You're probably realizing at this point, I could take any integer and put it over 1. Well, in that way, that makes all of the integers instantly rational numbers because they can be expressed in integer over integer form. So interesting. It's almost like there's a copy in some sense of all of the integers inside of the set of rational numbers. But let's notice something else as well. Notice that all of these natural numbers, well, these are also, each of these is also an integer. Notice there's a copy right there. But I could put each of these over 1. That would make it a ratio of integer over integer. So that means any natural number is instantly a rational number because it can be expressed in this way. So still part of our observation, let's say this is the collection of all rational numbers here. So inside of this little amoeba shape, let's say the rationals live here. But we said any number that's an integer is also a rational number. So there's a copy of the integers living inside of the rationals. But we also said that any number that's a natural number is also an integer, but also a rational number. So in this way, I want to define something. I want to define this notion of subset. So I'm going to say let A and B be sets. A is a subset of B. Denoted like this. A is a subset of B. If every element of A is an element of B. So this word turns out to be incredibly important. So in order for A to be a subset of B, every single member of A has to be a member of B. So just as a little example, I could say that the set containing 1, 2, 3 is a subset of the set containing AB 1, 2, 3, 4, 5. How do I know that this set is a subset of this set? Because every element in this set is an element of this set. So yeah, 1 is an element in this set, 1's an element in this set here, etc. So nothing can be left out. That's the important idea of this word every, this sort of universal quantifier, we call it. So yeah, every element in this set must be an element of this set in order to have this subset relation. Okay, well, if that makes sense, then we could sort of say something here. We said that every element of the natural numbers is an element of the set of integers. But we said that every element of the integers lived inside the rational numbers. So we get this following chain here. So this sort of symbolically says what this is hinting at. Every element of n is an element of z. Every element of z is an element of q, and therefore every element of n is an element of q. So we could go much, much further into this. I just need to develop enough set theory so that we can be careful when we talk about things in PreCalculus. Okay, there's a couple more classic number sets we need to get our hands on, but before we do that, we want to introduce this idea of intersection and union. Essentially, these are two set operations. It's a very common theme in mathematics that when you're presented with a new object, in this case, like sets, you want ways to create new sets. You want ways to combine them. Just like when you studied addition, you had numbers, but you then defined addition to create a new number. So given any two numbers, via addition, it pops out another number. Classic theme in mathematics. Presented with a new object, we want ways to combine these to get even more new objects. Okay, so let's start with the following. I'm going to say let A and B be sets. So when I refer to A and B, we know they're sets. They're well-defined collections of objects. So one, we're going to define the intersection. So the intersection of A and B is defined as follows. So the intersection of A and B is equal to the set of all elements X such that X is in A and X is in B. So this is the set of all elements X such that X is in A and X is in B. So what does that mean? This is the set of all elements that are common to both A and B. So for example, if A is the set containing, let's just say 1, 2, A, B, C, D, and B is the set containing 3, 4, and C, then what's A intersecting C? So we want to collect all of the elements X such that that element can be found in set A and set B. Well, if you look around, there's only one element in this case that's common to both set A and set B, and that would be C. Notice that when we define the intersection, the result is a set. So I would never just write, oops, did I write A intersecting C? That should be B. Get that before the comment section goes nuts. There we go. Okay, so A intersecting B, this is the set containing C. So whenever I compute this intersection, the result is a set. I would never just write the letter C here. Just a heads up in mathematics, when we have a set containing one element, we call that a singleton set. So this is actually the singleton set of C, set containing one element. Okay, great. So intersection, yeah, it looks at two sets and says, okay, what's common to both sets? Now, what about this case? If A is equal to the set containing 1, 2, 3, and B is equal to the set containing X, Y, Z, what's the intersection of A and B? Well, these two sets, they don't share any common elements. So their intersection is empty. We denote that with the empty set. Okay, so we want to now define union. The thing you have to be very, very careful of is with intersection, remember this goes with and let's see if we notice something about union. Okay, so the union of A and B. So the union of set A and set B. So A union B is equal to the set of all elements X such that X is in set A, or, so be careful, X is in set B. Now, or is a bit of a strange matter in mathematics. It doesn't quite mean what it means in everyday talk. So in math, Or means one or the other or both. So this side note is informal. So in math, or means one or the other or both. It's the or both that makes it kind of strange when you compare it to everyday speak. I mean, one would never say, I'm getting married on Monday or Tuesday and have someone assume that it could be both, right? But in math, that could happen. So what does this mean for us? It means that if an element is in set A or set B or both, then it belongs to the union of the two sets. Okay, so let's say if A is equal to the set containing 2 and 5, and B is equal to the set containing 2, 3, 4, then A union B, let's see here, we want the collection of all x's such that x is in A, or, that's a math or, x is in B. So we want the elements that are either here, here, or both. Notice that the 2 is in both, so it belongs to the union, but with repetition, we only write it once. So 2 goes in the union. 5 goes in the union, as well as 3 and 4. It turns out that order doesn't matter in a set when it's written like this. But if you wanted to, you certainly could write it in order. It wouldn't be wrong for you to write the 5 next, the 3 and the 4. In fact, any shuffling or permutation of the elements in here is thought of to be the same set. So let's bring this back to before, right? We were talking about intersection before this. Let's compute the intersection just to make sure that's fresh in our minds. So what would be the intersection of these two sets? What elements do these two sets share? Well, just 2, so I've got another singleton set. The intersection is not always a singleton set, so be careful. It just happens. This happened a couple times. Okay, so let's briefly review our classic number sets and then start to add some more classic number sets. Now, first we talked about the natural numbers. That was the set containing 1, 2, 3, 4, etc. Then we talked about the set of all integers. That, in some sense, fixed the closure under subtraction problem. Then we talked about a set that was a little bit more complicated, right? That was the set of rational numbers. This was the collection of all numbers that could be expressed as ratios of integers. So that's the collection of all objects R, or elements R, such that R is equal to A over B, where A and B are integers. However, B can't be 0. Okay, so when I define this, this is just in the context of these 3 sets. There's a better way to define this once we know some more math, but just in the context of these 3 sets. So just maybe imagine just for a moment that no other classic number sets exist but these 3. That's not true, but just imagine that. Suppose that's true just for a moment. If that were true, I'm going to put a little star here. Our irrational numbers, well, it's just sort of the logical negation of this. These are all the numbers that can't be expressed as ratios of integers. There's a caveat that these are also real, but I haven't quite defined that yet. Okay, so yeah, I haven't quite talked about this yet. But for the sake of sort of future math, when you go back to your notes, you can look at this in context and say, okay, under this sort of context, that's okay. So with the understanding that this is just in the context of these, we can now define the set of real numbers. This is a very loose definition. To actually define the set properly, you actually need to go through an entire course called Real Analysis, which does this with much more care and rigor. But this loosely gets at maybe a glimpse of the flavor, but it's not completely the full picture. So this is R bar. And so this is the union of the set of rationals and the set of irrationals. And it turns out a better way to say this is to say it's the set of all reals, but you take out all the rationals. That's actually a much better way to say this. But for now, I think that's sufficient. So if you're a math major, you will be able to define the set with more care if you take a course called Real Analysis. And it turns out that these numbers are actually have something to do with sequences and a calculus operation called a limit. And then finally, what we want to talk about is the set of all complex numbers. And I think I'm just going to put a little caveat here. Properly defined in a course called Real Analysis. Okay, so the set of all complex numbers, this is going to be C bar. This is the collection of all numbers, let's call them Z, such that Z can be expressed in A plus BI form, where A and B are real, and I is equal to the square root of -1. We'll give some examples of these complex numbers. So 3 plus 4i, that belongs to the set of complex numbers. Why? Because it's in the form of A plus BI, real plus real times I. Negative pi plus 3/10 I. That certainly belongs to the set of complex numbers because it's in the form of real number plus real number times I. Now I've got a question for you. What about this number here? So what about -4/7? Is that considered to be a complex number? Am I able to write this in A plus BI form, real number plus real number times I form? Well, it turns out I can. Because I can write this, in fact, I can do this with any real number. I can write this as -4/7 plus 0 times I, and that would be an A plus BI form. So because this is true, that means that -4/7 is a complex number. So yeah, any real number is also a complex number, or belongs to the set of complex numbers. So we get the following chain of subsets. So the set of natural numbers, we said earlier, is a subset of the set of integers. And the set of all integers is a subset of the set of rational numbers. But every rational number is a real number. And every real number, by this sort of argument of being able to write an A plus BI form, is a complex number, so we get this chain of subsets. So this lives inside of this, which lives inside of this, which lives inside of this, which lives inside of this. Now, as you're studying pre-calculus and calculus, there are some really, really important subsets of R that we want to talk about called intervals. These are not the only subsets of R, but they're really, really important subsets of R when you're defining functions. So yeah, let's talk about this. Let's transition into talking about this interval notation. And again, these are subsets of the set of all real numbers. Okay, so I want to start this off in a very particular way. I'm going to say let A and B be real numbers with a particular property. I want A to be strictly less than B. Okay, so now I'm going to sort of divide this up. So I want to talk about a particular set in mostly set builder notation. Then I want to talk about how to express that set as an interval or in interval notation. And then what does this look like geometrically, or what does the graph look like? Okay, so the first set I want to look at is the set of all elements x such that, well, first x is a real number, and there's a second property. I only want to consider real x's that are between a and b, strictly between a and b. So x is strictly larger than a, and also x is strictly less than b. So yeah, this is the collection of all real numbers that are strictly between a and b. As an interval, we denote it like this. Be careful not to get this confused with ordered pairs. You just have to deal with this in context. So in the context of intervals, we write it as this open interval. This sort of soft parenthesis here means we're not including a, so a gets excluded. This soft closed parenthesis means that b is getting excluded as well, so we don't consider b, but it's all the real numbers between a and b. We denote this exclusion on the endpoints with an open circle. And so, yeah, this is the collection of all x's that are real that are strictly between a and b. Okay, for our next set, let's consider the set of all x's that are real, where x is greater than or equal to a, yet strictly less than b. So here we want to include a, exclude b, and we want all the elements between. So here's how we include the endpoint with this notation, this little bracket. And we exclude b with a soft parenthesis. If we're including a, that point gets filled in. But since we're excluding b, that's open. Well, we can play a similar game by sort of swapping the roles where we exclude a but include b. So that would be the set of all x's such that x is real and x is strictly larger than a but less than or equal to b. Okay, so we want to exclude a but include b. So that means we want an open circle at a and a closed circle at b. And can you imagine the next case? Well, the next case, we just consider including both endpoints. So that's the set of all x's such that x is real, and x is greater than or equal to a, but less than or equal to b. And in this way, we include both endpoints. Okay, so let's look at some more interesting cases. Let's now consider the set of all x's such that x is real, and x is strictly less than b. So we want the collection of all real numbers that are strictly less than b. So it looks like we're going to be decreasing forever, and we denote that in this way. Now, when we deal with infinities in this course with intervals, that'll always be open. So how do we graph that? Open at b, but going forever to the left. Forever to the left we'll denote with an arrow. Okay, so we can consider something similar with the following. So let's consider the set of all real numbers x that are strictly larger than a. So that should look like this, right? Because we're going forever beyond a. And so here's a going forever to the right. And then we could have a couple more cases where we include the endpoints, right? So those will be very similar to these, but including the endpoints. So the set of all elements x that are real, but let's say x is less than or equal to b. So yeah, similar to this, but we, in this case, include b. So there's b, and we go forever to the left. Okay, so we've got a case similar to this one here. So the set of all x's such that x is real, and x is greater than or equal to a. So that would look like exactly this. And then lastly, the entire number line, which would be the set of all real numbers, we denote it like this, the open interval from minus infinity to infinity. And that extends forever in both directions. Okay, so let's look at some examples. Okay, so again, we'll do, how about set builder notation, the interval, and the graph. So for the first one, let's consider the set of all x's, where x is a real number, and x is greater than or equal to 0, but x is strictly less than 5. So how would I express this in an interval? Well, we'd want to include 0, but exclude 5. So it looks like this. And as a graph, well, since we want to include 0, that should be closed. But since we want to exclude 5, that should be open. Okay, so let's try the next one. I think for the next one, what I'm going to do is I'm going to give you the interval, and I want you to fill in both of these. So why don't you take a moment, pause the video, and try that out. Okay, so assuming you've done that, let's go over this. Let's see here. So this is, we want to exclude 3, so that's a strict inequality. And we want to exclude 4, that'll also be a strict inequality. So hopefully for number 2, you've got the set of all x's such that x is a real number. And let's see here, x is strictly greater than -3, and x is strictly less than 4. And let's see how you did on your graph. So we want to exclude both endpoints, so it should look something like this. Okay, for the last one, I think I'll give you the graph, and you can come up with the set and the interval. There's the number pi. Okay, so take a moment, pause, and fill these out. Okay, so let's see how you did. So as an interval, you should have closed here because that's closed, so that's going to include the endpoint, and going forever to the right, we denote like that. How about our set in set builder notation? This is the set of all x's such that x is real and x is greater than or equal to the number pi. Okay, so let's try some that are a little bit more complicated. So for each of these, we'll be given the set in set builder notation, and we'll have to figure out how to express this in interval notation. So I'm going to say express the following. Using interval notation. And so for the first one, we have the set of all x's such that x is real. And let's see here, x is less than or equal to -1, or, so there's our twist, x is greater than or equal to 3. Now, if you're unsure, I want you to consider maybe a graph. So if you look at that and you're not quite sure how to express that in interval notation, maybe we could get a graph out of this. Let's see here. So maybe I'll put a little number line here. Let's see here, 0, 1, 2. So this is the real number line. So the understanding is all the decimals that are packed between are represented there. Then this is complete. This is complete and filled in. And let's say that's -1, -2, -3. Now for this portion, we want all the elements, all the x's that are less than or equal to -1. So that's going to be closed. And then you'd go forever to the left. I'm going to bold that in a bit. And then here you want all the x's that are at least 3, right? So I want to include 3 and I want to go forever to the right. So maybe, yeah, that's a good thing to think about. If you're stuck, maybe a picture can help. Okay, so let's think about this. We're interested in x's that live here or here. Well, I know that or goes with union, so it looks like I'm interested in the following. So for interval notation, -infinity, because it's going forever to the left, it's going to stop at -1. We want to include that because of the closed circle. Or, so union, we're interested in elements that are at least 3, and we're going on forever here. So we've got the union of 2 intervals. So let's try the following. So let's say we want to express the following set in interval notation. Let's say we've got the set of all x's such that x is real, but x is not equal to 4. And I'm going to do the same thing. Instead of jumping immediately to interval notation, let's draw a graph. Okay, so our graph is the number line again. And we want every real number except for 4, right? So the collection of all x's that are real, but not 4. All the reals, but not 4. So not 4 means open circle at 4. I want everything to the right of it, everything to the right of 4, and everything to the left of 4. Do you see? It's almost like a mathematical hole punch. It's as if someone just went click and put a hole there at 4. So how do I say I want all of these numbers? I want all of these numbers. So if an element is here or here, I'm happy, right? So in interval notation, we want minus infinity to 4 open because we don't want to include it. That was deleted, right? Think of our mathematical hole punch. It punched that out. So union 4 to infinity. Notice that this is a clever way to omit a point. Let's try another. Let's say we want the set of all x's such that x is real, but x is not equal to plus or minus the square root of 2. So I think based on our previous example, you're pretty hip to what's going to happen. Think about your mathematical hole punch. There should be an open hole at negative radical 2 and another open hole at positive radical 2. So it shouldn't be a surprise, and if it is, draw a number line, that we get the following in interval notation. Okay, so this is how we're going to omit our radical 2, or negative radical 2 rather. But we also need to omit positive radical 2. So notice I get the union of 3 open intervals. Notice that when I delete 2 points, I get 3 intervals. Notice that when I deleted 1 point, I get 2 intervals. You can kind of come up with a pattern for that. If I delete n points, I should have n plus 1 intervals being unioned. Okay, let's do one more and we'll call it a lecture. So let's say we've got the set of all x's such that x is real and x is strictly greater than minus 1/2 and x is less than or equal to 1, or x equals 3. So we're combining a lot of ideas here. Maybe this would be a good one for our number line here. Let's say here's 0, 1, 2, 3, 4. I like to go a little beyond. So I'll go to 4. And then here's minus 1. That should be good. So we want x to be strictly greater than minus 1/2. So let's say there. But we want it to be less than or equal to 1. So these elements, these real numbers, we definitely want. But we also want 3. So this reminds me of an interval. This reminds me of a singleton set, right? A set with one element. And the or reminds me of union. So in interval notation, we have the following. Notice that I don't write this. That's a singleton set. And this is exactly this set expressed as the union of two sets, an interval, and a singleton set, which is just fine.